Folks, exciting stuff, really exciting stuff. We're getting in to now the Helmholtz and the Gibbs. And this is exciting because in a lot of your classes, you've talked about Gibbs. You haven't talked about Helmholtz at all, but they're closely related to each other. But now we're going to see where these come from. And what we're also going to get into is our criterion for spontaneity. It's more than just delta S is greater than 0. There's a whole mess of other things that are required for spontaneous processes. And we're going to dive into that now. And we start with the Clausius Inequality, right? And I'll remind you that that is ds is greater than or equal to dq divided by t. I'm dropping all the reversible, irreversible. We're putting this together for general, for any case. Okay, this has to work, all right? And so rearranging this, we can say ds minus dq divided by t must be greater than or equal to 0. Okay? So now, we'll consider two different things. Heating at constant volume, which hopefully maybe you're thinking U, and heating at constant pressure. And hopefully from there, you're thinking H. So we're first going to start with U and H, and then we'll see the manifestations for G and A, for Gibbs and Helmholtz. Okay? So we recall heating at constant volume, so dqv gives me du, because there's no work done, so the work is 0. Okay? And so now considering this relationship right here, if I'm talking about constant volume, then that means that I can rewrite this as ds minus du divided by t, all must be greater than or equal to 0. And doing some algebra here and rearranging, I can say t ds must be greater than or equal to du. So I added that over to the other side and multiplied by t all the way through. So TDS must be greater than or equal to du. Okay, well, what if we now talk, let's think about this ds, okay? And suppose we know that that is ds. We've already imposed constant volume. So what if I said constant internal energy? Well, that means this du is going to become 0, and thus, this is what I call a criteria for spontaneity. Okay? At constant volume and constant internal energy, ds must be greater than or equal to 0. Well, we kind of already knew enthalpy had to be greater than 0 for a spontaneous change. But now what's the manifestation for U? Okay, well, what if we say now du? We're already talking about constant volume, but now what if I switch it? What if I make it constant entropy? Okay, well, that would mean that this chunk becomes 0, and 0 must be greater than or equal to du, or in other words, du at constant volume and entropy must be less than 0. Okay, and also, hopefully what you gather from this, what you see, U, natural variables become V and S from that thermo square. Beautiful. Okay, what about heating at constant pressure? Well, we know dQp equals dH, okay? And so I can rewrite the Clausius inequality as ds minus dH over t greater than or equal to 0. Okay, and so once again, we know the quantity TDS must be greater than or equal to dH. All right? And now if we impose these conditions, so for example, we know ds, we've already said at constant p, but what if we now make that constant h? Okay, well then, let's see, that's got to be greater than or equal to 0, right? Or if we said dh, still at constant p, but now what about at constant s? That's got to be less than or equal to 0. Okay, so once again, increase in entropy for a spontaneous process, but we also see that enthalpy must be negative at constant pressure and entropy for a spontaneous process, okay? And we also see the connection now of enthalpy with pressure and entropy, okay? So what about these other quantities, okay? Well, Helmholtz, by definition is the following, okay? A, 1, 2, 3, U minus TS. So it is the difference between internal energy and temperature times entropy, okay? Well, we know that basically the quantity TS really gives us heat, okay? So in other words, I can say dA equals a du minus T ds, okay? Well, recall ds is Q over T, okay? So TdS really gives us heat. So that means this definition, U minus TS, it's work. It's where we get the name, the maximum work function, okay? And so now considering our Clausius inequality, TdS must be greater than or equal to du. So now let me rewrite that. I'm looking at that and I'm like, I don't even know what it says. du, okay? So once again, the quantity T ds, right, is really giving us heat. So when we talk about the difference, U minus Q, that has to be W, right? Because we know U equals Q plus W. So this is where we get the name maximum work function out of the Helmholtz free energy, okay? So now considering that dA equals du minus TdS, and TdS has to be greater than or equal to du, okay, then what we know for this process to be spontaneous, ds has to be positive, okay, du has to be negative, and so thus, or excuse me, if I start thinking of now, let's hold temperature constant, okay? And as it turns out, I'm doing a terrible job describing this, but as it turns out, also at constant volume, this quantity has to be negative, okay? And so the reason for the constant volume is because now we're saying at constant volume, work will be equal to 0, okay? And if du has to be negative for that spontaneous process, then at a minimum, dA dt dV has to be less than or equal to 0 for a spontaneous process, okay? And then similarly for Gibbs, all right, Gibbs is defined as H minus TS, which we also once again recognize is work. That's what this is, okay? It's the maximum work function, all right? And so now that means, I know where the constant volume, the constant volume comes from the fact that we're dealing here with U, okay? So now with Gibbs, because we're dealing with H, we need constant pressure, okay? So that comes from now TdS greater than equal to dH. And because now we're talking about dH, constant P and du is constant V. Okay? And so now similarly what this gives us is dG at also constant T, if I drop off that T right there, but now at constant P, this has to be negative for all spontaneous processes. And hopefully you remembered that from your Gen Chem or even your biochem, Gibbs has to be negative for a spontaneous process. Okay? So a few more words on this. So let's see here. What about in the case of when these are equal to 0? Okay, so when dt dv equals 0, or when dg at constant p equals 0, this is a special condition in chemistry that we call equilibrium. And we will spend a whole module on the thermodynamics of equilibrium. But this gives us the thermodynamic basis of equilibrium. When these quantities are negative, that gives us a spontaneous process. And because of these relations of the first law, both of these quantities are often referred to as the work function or the maximum work function. Okay? So I do want to spend a little bit of time describing where the alternative name for these comes from, the free energy. Why is it called Gibbs free energy? And oops, so as a reminder, sorry, I forgot I had this reminder slide. Here are all of our criterion for spontaneous processes. You should know these, okay? dg, dA, dH, du, all at their constant respective natural variables must be negative for all spontaneous processes. And of course, entropy must increase, must be positive for all constant processes, okay? So now I'm going to set up a scenario. I'm going to set up two scenarios here, and Adkins describes these. Admittedly, it's a bit confusing, but I really like this description of why we call this the free energy. Okay? So this first starts by saying, suppose we have a system. And in this system, we're going to say, suppose that delta U of the system is negative and delta S of the system is negative. And we're going to put together what needs to happen for spontaneity. Spontaneity, okay? And we'll impose that this is the first condition we're going to look at. If the internal energy of the system is decreasing, which is what we'd expect for spontaneity, but suppose that the entropy decreases, could this still be spontaneous? How would we do it? Okay? Well, one thing that we note is for all spontaneous processes, delta S total equals delta S system plus delta S surroundings, and that must be greater than 0 for this process to be spontaneous. So we know right off the bat, if the change in entropy of the system is negative, it can still be spontaneous as long as the change in entropy of the surroundings is greater than the absolute value of the change of the entropy of the system. So in other words, we know that the entropy change of the system is negative, but if I look at the absolute value of that and compare it to the entropy change of the surroundings, and this relationship is true, then I will have a spontaneous process, okay? So now how do we achieve this? How do we achieve that the delta S of the surroundings is going to increase if the delta S of the system is going to decrease? How do we do it? Okay, well, let's first look at A. So all of this is with respect to A, Helmholtz, but it's the same situation for G, the same situation for Gibbs, okay? So we know that delta A is delta U minus T delta S, okay? And we also know for this to be spontaneous, it's got to be less than or equal to 0, that whole chunk, okay? So, or in other words, what we could say, applying the system to this, we could say delta U of the system must be less than or equal to T times delta S of the system, okay? And so because we also know that both of these quantities are negative, the change in entropy of the system cannot, times temperature, cannot be as negative as the delta U, okay? And so what that means is the following, okay? So I'm going to expand through this, and I'm going to say dA equals du minus, we recognize that all of that is really dq, which equals dw less than 0. If dw is less than 0, that tells us the work is having to be done from the system to the surroundings, and that's exactly what you can see in this arrow. The system is working on the surroundings. So that's one condition that has to be met for all of this to happen, okay? And you'll also notice there's this condition here that says, well, the work has to be less than the change in internal energy. And that's true because of this relationship. The delta S has to be less than the delta U because of the way this inequality, or excuse me, it has to be less negative than is the change in U, okay? And so what that means is we cannot supply the same amount of work as we have in internal energy, right? So the work supplied has to be less than the change in internal energy. And so what that also means, to make this condition happen, to generate enough change in entropy in the surroundings to keep this process spontaneous, dq has to be much greater than dw, right, to make this happen, okay? That's how this is going to be negative, right? The dq has to be greater than the dw to make this happen, okay? And it's also going to have to be positive, right, for this to be satisfied. And so in other words, we also then see that a large amount of heat, a really large amount of heat, must be evolved out to the surroundings to generate enough spontaneity to overcome the reduction of entropy in the system, okay? And so what's happening here is, Atkins puts it very nicely, nature is demanding a tax on you as it's converted into work. And the tax on that is the free energy, okay? It's the part of the change in internal energy we are used to do, we are free to use for work. And this large amount of heat that has to exit the system into the surroundings is that required component of spontaneity, right? We talked about this with the Kelvin statement of the second law. If our system is going to do work, it has to evolve a ton of heat spontaneously out to have enough entropy change in the surroundings to be spontaneous, okay? What about another situation? Well, let's impose that delta U system is less than 0 still, but what if now the change in entropy of the system increases, okay? So it's looking good so far for spontaneous, right? We should just say, well, right away that should be spontaneous. But now what are the physical observables when this happens? So what happens if we have a reduction of entropy in the system as well as an increase of entropy in the system? Excuse me. What are the consequences? Okay. Well, the consequences are that we still have delta U system is less than or equal to T delta S. So this comes from our Clausius inequality. Okay. And so we can see that this is true, that the delta S system will be greater than the delta U system. It's a positive quantity and that's a negative quantity. So that's all good there. Okay. We can also see by relation dA equals du minus dq, which equals dw And now this is where this gets to be a little tough to gather, because this still has to be negative for this to be spontaneous. Okay? So dW still has to be negative. And that means that it has to be evolving work. The system still has to be doing work on the surroundings. Okay? But this seems a bit paradoxical, because if the system is doing work on the surroundings, there should not be a decrease in entropy of the system, or there should be a decrease in entropy of the system, just like in this scenario, right? When the system works on the surroundings, there usually has to be a decrease in entropy, because we're exchanging orderly motion for heat, right? Work is orderly motion. When we do work, we're doing something that's more orderly, okay? So there should be a decrease in entropy, but there's not. There's an increase of entropy in the system. And why is that? Well, that is because in order for this to happen, heat has to flow into the system. That's what's going on. You saw the picture there, but I didn't leave it described, okay? In order for this to all be spontaneous, right, delta S system equals Q divided by T, which we know is greater than 0, which tells me dQ had to be greater than 0, which means heat has to flow into the system to make this work happen. And even though this seems a bit paradoxical, the way that we can describe this is nature is now providing a tax refund. And that tax refund is the free energy. It's the change in internal energy that we are free to use as work. Okay? So the big picture here, all right, the big picture of what's going on, let me back up here. Where are my equations? Let's see here. Yes, so this is the big picture that's really going on, right? We know that Helmholtz is the difference between internal energy and TDS. So in other words, it is the difference between the internal energy of the system and the heat supplied to the system, okay? And when that quantity is negative, that quantity is free for us to use. It's the free energy, okay? It can be used for chemical changes or physical changes. And when we recognize that these quantities are negative, nature is providing us a tax refund that's giving us free energy that we can use as work, okay? That is the origin of the name free energy. So Atkins has some lovely prose on this. If I didn't quite do it for you, if you're still left kind of confused by this, take a look at pages 115 through 117 in Atkins. That's where this picture is, and he has a really nice set of paragraphs describing it, okay? So I'm just going to talk about standard molar Gibbs energy. And then after this slide, I'm going to end the video because I'm liking how these quick lectures go, okay? And so I'm just going to talk about standard molar Gibbs energy very briefly. So it's just like all of our other chemical quantities, right? So delta G of, let's say, a chemical reaction, right, we know is the sum of the free energy of formation of the products minus the sum of the free energy of formation of reactants. So like that classic Gen Chem stuff. But what I really kind of wanted to get into with this, so we note that also delta G of a reaction, we can write, I'll put the 0 there for standard. We can write delta H minus T delta S, this relationship that we've been talking about. And what we really recognize, we should really recognize that this is dW. This is work, okay? So let's look at something like carbon dioxide, negative 394.4. Okay, so what this is saying, when we take carbon and oxygen and form carbon dioxide, so that's what this molar Gibbs free energy means, formation of the elements from their standard states. Okay, it's spontaneous, right? Negative 394.4, hugely spontaneous. Okay, that doesn't mean that it's going to happen quickly. Thou shalt not mix kinetics with thermodynamics. They often maybe correlate, but they don't necessarily propagate to the same thing. Like if something has a large delta G, a large negative delta G, it doesn't mean that it's necessarily going to happen quickly. But what it does mean is if you have a bunch of carbon and a bunch of oxygen and a whole lot of time, undoubtedly, the carbon dioxide will form spontaneously. It will happen without you even wanting it to happen. And the bigger picture idea of that is nature is providing the tax refund on the internal energy as it is converted into work. Okay? So in other words, nature will force those electrons through the orbitals, in the case of this chemical reaction, spontaneously. Benzene, diamond, not so much. And that makes good sense for diamond, right? You know that you need a lot of pressure and temperature to make that happen. You're not going to form a diamond spontaneously from a lump of coal at 298 K. You need a ton of input. So you have to provide the taxes for that situation. Okay? So I'm going to cut it off there. And it will be one last video, a bunch of short and sweet 30-minute videos for this module. So what I have covered, just to remind you, so the criterion for spontaneity. So be familiar. So with the origin of the name free energy, it's confusing, and we could spend days and days and months and weeks talking about the free energy. So I just really kind of just touched on it. So just be familiar. Be familiar with standard molar Gibbs energies. So I think that's mostly like kind of a review from Gen Chem, but just recognize this idea, like negative delta G's means that this element will form spontaneously from its elements. Okay, so we were destined to have a carbon dioxide rich atmosphere and water in our atmosphere as well. Okay, and so the last two videos, I'm going to wrap this up, we'll be covering those learning goals 14 and learning goals 15. Okay, all righty, folks.